Okay, so in the previous videos we have defined real numbers, we have defined their addition and multiplication, and we have also embedded the system of rational numbers in the system of real numbers. We also saw that these operations are well defined. So the natural next thing to do now for us is to define negation of a real number, and then with the help of negation we will define subtraction. So we start our discussion like this. We define the negation minus x of a real number x as this, which is the product of minus 1 and x. But the reason we now only we are defining this is that we have now a way of identifying rational numbers as real numbers because of our embedding. So that's why you can think of this minus 1, which is a rational number, also as a real number, and that's why this product makes sense. Note that since minus 1 is rational and hence real, the product of minus 1 and x makes sense. Also, this definition of negation is consistent with the definition of negation of a rational number, say q, because minus q is also minus 1 times q. So if the real number originally it happens to be a rational number, then because of this identity which is already true in the system of rational numbers, and because of our embedding of the rational numbers into the real numbers, and because of the way we have defined negation for real numbers, the two things are consistent. There is no inconsistency between these two things. Moreover, if an is a Cauchy sequence of rational numbers, then its formal limit by definition of real numbers is a real number So if we want to find the negation of that formal limit, then by our definition this will be equal to -1 times formal limit of the sequence an. But we know according to our embedding that this rational number -1 can be thought of as the real number which is given by the formal limit of the sequence, all of whose terms are equal to -1. That means this is equal to times this formal limit. Now here if you apply the definition of product of two real numbers, then you get limit of -an, because -1 and an will be multiplied. Okay. Now that we have negation, we can use it along with addition to define subtraction. Now having negation, we can define subtraction of two real numbers x and y as this. X minus y is defined to be the sum of x and the negation of y. So that's how we define subtraction. Note that this implies that if an and bn are Cauchy sequences of rational numbers, then if we calculate this, then this will ultimately, you can see this we have already calculated and it turns out to be that formal limit. With that you have to add this real number. So doing everything that we are supposed to do, we will ultimately get this. Note that unlike addition and multiplication, here we are not saying anything about the substitution axiom being satisfied. The reason is that we are defining negation in terms of multiplication. Note this carefully. So that's why there is no need to verify the substitution axiom, because we have already verified it for multiplication, so automatically it is going to be true also for this particular case of multiplication, that is negation. And because we have already again verified the substitution axiom for addition, and using which and negation we are defining subtraction for. So for subtraction in general, the substitution axiom is satisfied, and it is these operations are hence well defined. Okay, now we come to a proposition which summarizes the algebraic properties of the system of real numbers. Along with this, that is the set of real numbers with these operations. All the laws of algebra. Okay, so this is proposition 5.3.11. All the laws of algebra from proposition 416 hold not only for the integers but also for the reals, or for the reals as well. So this is that proposition which tells us that the integers form a ring, that is so and so properties are true, namely the usual ring properties which we already have in the statement of proposition 416, saying that it is this system forms a ring is just a short way of saying that this list of properties are simultaneously true for the system. Like addition has to be associative, there must be an element that behaves like 0, every element has a negative, and things like that. Addition has to be commutative, such things. So we will have a proof which is actually not complete, in the sense that we are not going to show that all the properties are true. We illustrate this with only one of the properties, namely one of the distributive laws, which involves both addition as well as multiplication. But the way we will prove this, it will make the things clear, and you will see that the others can similarly be proved, and in fact this is way easier than what we encountered in proposition 416. There we had to do many things. Here the calculation is less. So this is somewhat paradoxical. Thinking of the real number system, thinking of these objects as defined using infinitely many rational numbers. Each real number needs infinitely many rational numbers for its definition. So these objects must be much more complicated than the rational numbers themselves. However, the whole system has been arranged in such a nice way that now that we have the real numbers and the many operations in this system, now the calculations are almost obvious. So let us see what we mean by these remarks. We illustrate this means illustrate this statement with the proof of this identity. It's one of the distributive laws, xy plus xz. We often express this relation by saying that multiplication distributes itself over addition. Okay, so in that sense it is distributive law. It's a basic relation that relates the two operations, multiplication and addition. For real numbers x, y and z. For real numbers means for any real numbers. So let x be the real number, means it will be some formal limit of some Cauchy sequence of rational numbers. Let x be this formal limit y be this formal limit and z be this formal limit Cn. An, Bn and Cn, these are Cauchy sequences of rational numbers. Then we directly calculate this quantity x times y plus z. This is x, and y plus z by definition of addition of two real numbers is this formal limit Bn plus Cn. Then by definition of multiplication of two real numbers, we get this An times Bn plus Cn. Now we already know that such a law is true for the rational numbers, and these An, Bn, Cn, these are all rational numbers. So we can write An Bn plus An Cn. I think now you can almost see that the things have been defined in such a way that such calculations will become almost obvious. The calculations themselves will become very natural. And in this calculation, we don't even have to cook up any elaborate strategies for handling a particular situation. You just let the calculation flow and see where it takes you. Now you again apply the definition of addition of two real numbers, and you can write this formal limit as a sum of these two formal limits An, Bn and An, Cn. This becomes equal to, again by the definition of multiplication, limit An times limit Bn plus again limit An times limit Cn, and this is just simply xy plus x z. That's it. It's that simple. Can be similarly proved. And in fact, I want you to prove the other laws of algebra, at least see that they are true. They may be this simple, but you just need to see them for once. Okay. So now now only one thing is left for us to do, the definition of reciprocation, which we already did in the case of rational numbers. If you remember, we defined a rational number as a formal quotient of two integers, right, where the second integer is not equal to 0. In the definition of reciprocation for such a rational number, that is the definition of this, provided the rational number itself is non-zero, that is a is not equal to 0, is this. So the thing was quite simple for rational numbers. However, here for real numbers the things are going to be complicated. With these things we have seen the simplicity of the system. Let us now look at its complexity. So the last basic operation we need is reciprocation. This one is a bit more subtle. The path we have so far followed has given us it has been quite easy. It was like a cakewalk. We had two formal limits. To define their sum, we just took the sum of the corresponding terms of the individual sequences. To define the product, we did a similar thing. We multiplied the terms of the sequence. To define negation, we defined it using multiplication, but ultimately it turned out to be like this. If you take the negation of this real number, then you just have to negate each term in that Cauchy sequence that defines the real number, and correspondingly subtraction also turned out to ultimately be of that form. However, if one follows the same path, and for this real number, say one defines reciprocation just like this. By taking reciprocals of the individual terms of the Cauchy sequence, then one encounters quite a few problems. So let us write this systematically. One obvious guess is to define like what we wrote just now. this. But this gives us problems. There are a few problems with this. For instance, you consider this Cauchy sequence. Let A1, A2, A3, etc. be this Cauchy sequence whose terms go like this: 0.1, 0.01, 0.001, and so on. And let x be the formal limit of this Cauchy sequence. That is, x is the real number determined by this Cauchy sequence. Then by the above definition, we have to consider the reciprocals of these real numbers, and we have to consider the corresponding sequence given by those reciprocals. By the above definition, x inverse is the formal limit of the sequence Bn, where B1, B2, B3, etc. is the sequence obtained by taking the reciprocals 10, 100, 1000, 10,000, and so on. Okay. But the problem here is that this sequence is not a Cauchy sequence, so it cannot have a formal limit. Note that the sequence is not Cauchy. In fact, if you want to verify that this is not a Cauchy sequence, ideally if you just use the definition of Cauchy sequence, you can show that it does not satisfy the definition, but a better way would be to see that a necessary condition for Cauchiness is violated. Namely, you look at the necessary things that any Cauchy sequence must satisfy. Any Cauchy sequence must be bounded. We already proved that when we discussed Cauchy sequences of rational numbers in the previous section, I think. So this sequence if it were a Cauchy sequence, it would have to be bounded. However, it is not bounded, because you can see that the terms are increasing in such a way. You can in fact show using a bit of mathematics that this is not bounded. It's not bounded. So this is one problem that we may encounter if we use that naive and crude definition of reciprocal. But there is another problem also. But before we go to any other problem about this approach, let us see why this problem arose here. Of course, the problem here is that the original sequence an is equivalent to the zero sequence where all the terms are equal to 0, and so the real number x is actually equal to 0. And we already know that the rational number 0 cannot be reciprocated. So that is the problem in this case, is equivalent to the zero sequence. And so x is equal to 0. So that's why it cannot be reciprocated, and this strange situation has arisen. We cannot, in fact, we are not supposed to be able to apply the operation of reciprocation to x simply because x is 0. However, there is another problem that can arise. Even if we restrict ourselves to non-zero real numbers, we may encounter problems. And for that, you consider this Cauchy sequence. Zero, 0.9, 0.99, 0.999, etc. In this case, the problem is of a different nature. You see that if you treat this as a, it is a Cauchy sequence of rational numbers, so it will have a formal limit. Say that formal limit is y, and in fact we can show that this sequence is equivalent to the constant sequence, all of whose terms are equal to 1, so that the formal limit of this Cauchy sequence will actually be equal to the rational number 1. So it's not a zero real number. Okay, so this problem is not present here. So we should be able to use the previous naive definition. But if you try to do that, in the very first term you encounter a problem. You will be considering the reciprocals of the terms of this sequence, but you cannot consider the reciprocal of 0. This is the rational number 0, so there is no reciprocal of 0. So even before finding the formal limit, the sequence itself, sequence Bn or An inverse itself cannot be formed at all because of this one term. In this case, our naive definition of reciprocal does not work because the reciprocal of the first term 0 does not exist. And now you can guess what sort of problems we may encounter if we have 0 in other places. You can think of getting rid of this 0 by simply just forgetting about it. But what will you do if 0 keeps appearing? I mean, existence of 0 inside a Cauchy sequence actually does not affect anything. If you replace this sequence with a sequence where, say, after every non-zero term you put one extra 0, then that sequence will be, you can show that sequence is actually equivalent to this sequence. So they will represent the same real number. If someone wants to use that sequence in our naive definition of reciprocal, then they cannot get rid of zeros because there are infinitely many 0 terms. So what to do? The way around this is a new definition. This one is quite clever. It's called sequences bounded away from 0. And the definition goes like this. Let me write here. A sequence An of rational numbers is said to be bounded away from 0 if there exists a rational number C which is positive such that the absolute value of each term An in the sequence is greater than or equal to C for all n greater than or equal to 1. So because of positivity of C and because of this inequality you can now see that in a sequence of rational numbers that is bounded away from 0, no term can actually be equal to 0, because we cannot have c less than or equal to 0. C is already greater than 0. So if we have c less than or equal to 0, trichotomy of rational numbers will be contradicted. So in such a sequence, 0 terms will not occur anywhere. Now let us see the next example. Consider the sequence. Note carefully that our definition of sequences bounded away from 0 does not say that it has to be a Cauchy sequence. It's a different definition, independent of Cauchiness. Consider the sequence -1, 1, -1, 1. So the terms alternate between -1 and 1, and it goes like that. It's bounded away from 0. Why? Because the absolute value of every term is equal to 1. So this c we can choose in this case to be equal to 1. In fact, we can write the absolute value of each term is greater than or equal to 1. Let's take another one. The sequence (0.1, 0.01, 0.001, 0.0001, and so on) is not bounded away from 0. Bounded away from 0 means there is a limit to how small the terms of the sequence can be. Here, however, the terms are getting smaller and smaller in size or magnitude without any such lower bound, without any such limit. So that's why it is not bounded away from 0. In fact, the reason it is not bounded away from 0 is that this sequence is equivalent to the 0 sequence. So that is why it is not bounded away from 0. And neither is the sequence this sequence. (0.99, 0.999, etc.). The reason for this sequence not being bounded away from 0 is the first term. Note that as you go down the sequence, as you go further and further along the sequence, the terms actually increase in size. 0.9 is strictly less than 0.99, which is strictly less than 0.999. So if the first term were not there, then that sequence would have been bounded away from 0, because all the terms will have absolute value greater than or equal to 0.9. However, 0 cannot have absolute value greater than or equal to some positive rational number. So because of that very first term, we cannot, this is not bounded away from 0, and that's why you can see that if in such a sequence you have even one 0 term, it fails to be bounded away from 0. So that's how this definition avoids such sequences where 0 terms can appear, and neither is this sequence. The sequence in 100, 1000, etc. is bounded away from 0. Because the absolute values of all the terms are greater than or equal to 10. So for this sequence, you can take c equal to 10. But is not bounded. Recall the definition of boundedness. According to that definition, this is not bounded. So bounded away from 0 is one thing, and bounded is an entirely different thing. Okay, now here is a lemma that shows why this definition is important. Lemma 5314. Let x be a non-zero real number. Then x is equal to the formal limit of an for some Cauchy sequence an of rational numbers that is bounded away from 0. So because x is a real number, we already know by definition of real numbers that it's the formal limit of some Cauchy sequence. However, that Cauchy sequence may not be bounded away from 0. It may even have 0 terms. But if x is non-zero, then you will get a Cauchy sequence which may not be the original Cauchy sequence used to define x, but it will be a Cauchy sequence of rational numbers that is bounded away from 0, and that in fact its formal limit is also equal to x. In other words, this new sequence will be equivalent to the old Cauchy sequence. So such a sequence always exists for every non-zero real number. That we need to now prove. Okay, since x is real, there exists a Cauchy sequence Bn of rational numbers such that the formal limit of Bn is actually x. Okay, but it's also given that x is not equal to 0. So that means this Cauchy sequence cannot be equivalent to the 0 sequence, since x is not equal to 0. The sequence Bn is not equivalent to the 0 sequence. Being equivalent means what? Being equivalent means for every rational number epsilon greater than 0, these two sequences are eventually epsilon close. Being not equivalent will then mean that there exists at least one rational number epsilon greater than 0 such that these two sequences are not eventually epsilon close. Thus, there exists a rational epsilon greater than 0 such that Bn and 0 are not eventually epsilon close. Let me put some ink. So this epsilon is some epsilon, okay, it's not all epsilon, at least one such epsilon is there. Fix this epsilon. So now this epsilon is fixed for us. Now we are going to use the fact that Bn is a Cauchy sequence along with this particular value of epsilon, since this is a Cauchy sequence there exists an integer, so you just apply the definition of Cauchiness such that the distance between Bm and Bn is less than or equal to epsilon for all m and n greater than or equal to n. Okay. For technical reasons, let us take this epsilon by 2. Epsilon by 2 is also a rational number, so you can consider that. In place of epsilon, you can choose, say this is a new value of epsilon by 2. Since okay, so now we are going to use the fact that Bn and 0 are not eventually epsilon close. Since Bn and 0 are not eventually epsilon close, we cannot have absolute value of Bn which is equal to absolute value of Bn and 0 to be less than or equal to epsilon for all n greater than or equal to n. Because if this happens, then by definition of eventual epsilon closeness, this too will be eventually epsilon close, but that is not possible. So this cannot happen. Absolute value of Bn cannot be less than or equal to epsilon for all integers n greater than or equal to n. This means there exists an integer, say n naught, which is greater than or equal to n, for which the corresponding Bn term has its absolute value strictly greater than epsilon. Okay. Now for any integer n greater than or equal to n, we have, now watch this calculation, epsilon minus absolute value of Bn, epsilon minus absolute value of Bn is less than this. So what we have done here is that we have subtracted absolute value of Bn from both the terms in this inequality. That will give us this. Now this is a real number. Well, it's real number means it's a rational number. So we already know from properties of absolute value of rational numbers that any rational number is less than or equal to its absolute value. Okay, and this turns out to be, this turns out to be less than or equal to the absolute value of bn naught minus bn. Why is that so? That we will give its justification, but let us complete this series of inequalities. Now you look at this. The n we have chosen is greater than or equal to n, and n naught is also greater than or equal to n. So by the definition of Cauchiness, we can take n naught in place of m, and n of course is n. So this will be less than or equal to epsilon by 2. Now we write the justification for this inequality. The inequality follows from proposition (433)b. If you go to this result, looking at what the statement is here, you will automatically understand how this inequality follows from this part B of the proposition. So what do we have now? Ultimately, epsilon minus absolute value of bn is less than or equal to epsilon by 2. From this, if you calculate, you will get this. This is greater than epsilon by 2. For what? For which n? For all integers n greater than or equal to n, because for such integers we are doing the calculation. Okay, now define a sequence as an is defined to be equal to epsilon by 2 if n lies in this range, and is defined to be equal to bn if n is greater than or equal to n. Okay, this is a new sequence. Bn is the sequence that came from the real number x. The formal limit of bn is x, but now after doing all these things, we are defining a new sequence an. Note that an differs from bn, from the sequence bn, in only these first n minus 1 terms. That is, if you write the terms of the sequence an in that order, then it will look like this. However, if you write the terms of bn, then these are the terms of bn. So do you see one thing from these two sequences? The first thing is that since bn is a Cauchy sequence, this sequence an is also a Cauchy sequence. Why? Because an and bn are eventually, after this stage or starting from this stage, exactly the same. So since bn is a Cauchy sequence, an also must be a Cauchy sequence. If you really want to use the definition, then definition of Cauchiness just simply says this, that for any epsilon greater than 0, there exists a positive integer m, which you can conveniently choose to be greater than or equal to n, such that bm minus bn, this distance between bm and bn, is less than or equal to epsilon for all m and n greater than or equal to m. But because of our choice of m, this m and n will also be greater than or equal to n, and because of this sameness, this is nothing but am and an. So an is also a Cauchy sequence. In fact, an is not just Cauchy, but the sequences an and bn are actually equivalent, because they are not just eventually epsilon close, but you can say they are actually eventually the same. After this stage, they become identical. So these are the two things we are now going to conclude. One can clearly see that an is a Cauchy sequence since bn is a Cauchy sequence, and in fact an is equivalent to bn. Now because bn is a Cauchy sequence, and an is equivalent to bn. So if that happens, what can we say? So because of this equivalence, the original real number x is also the formal limit of an, but an is not just any Cauchy sequence, it has a property. Note that absolute value of an is greater than or equal to epsilon by 2 for all positive integers n. If this n lies between 1 and capital N minus 1, then absolute value of an is equal to epsilon by 2, because all such terms are actually equal to epsilon by 2. And if this n is greater than or equal to capital N, then absolute value of an becomes absolute value of bn, because that's how we defined an. And we have already proved that absolute value of bn is greater than epsilon by 2 for such choices of n. So our new sequence an, whose formal limit is also x, is a Cauchy sequence that is bounded away from 0. That was what we wanted to prove. So an is bounded away from 0. So here the proof ends. Now using this fact, one can now define the reciprocal of a non-zero real number, just like how we used that ninth definition. However, instead of using the sequence Bn for the real number x, we are now going to use this new sequence an, which is bounded away from 0, and so it will not give us those problems that we previously encountered. This, however, we will do in another video, because after this also there are some things. So I end the video here. If you have any doubts regarding this video or any other matter in mathematics and related subjects, then you can always write in the comment section. So that will be all for tonight. I sign off. So this is me, Lucifer, from a mathematical room. Have a nice night.